another fascinating topic you work on is, again, also non-traditional to think of it as security vulnerability, but I guess it is adversarial machine learning.
Mm-hmm.
Is basically, again, high up the stack, being able to attack the accuracy, the performance of machine learning systems by manipulating some aspect. Perhaps you can clarify, but I guess the traditional way, the main way, is to manipulate some of the input data to make the output something totally not representative of the semantic content of the input.
Right. So in this adversarial machine learning, essentially, the goal is to fool the machine learning system into making the wrong decision. And the attack can actually happen at different stages. Can happen at the inference stage, where the attacker can manipulate the inputs, add perturbations, malicious perturbations to the inputs to cause the machine learning system to give the wrong prediction, and so on.
So just to pause, what are perturbations?
Also, essentially changes to the inputs, for example.
Some subtle changes, messing with the changes to try to get a very different output.
Right. So, for example, the canonical, like adversarial example type is you have an image, you add really small perturbations, changes to the image. It can be so subtle that to human eyes, it's even imperceptible to human eyes. But for the machine learning system, then the one without the perturbation, the machine learning system can give the correct classification, for example. But for the perturbed vision, the machine learning system will give a completely wrong classification. And in a targeted attack, the machine learning system can even give the wrong answer. That's what the attacker intended.
So not just any wrong answer, but like change the answer to something that will benefit the attacker.
Yes.
So that's at the inference stage.
Right.
So yeah, then, what else?
Right. So attacks can also happen at the training stage, where the attacker, for example, can provide poisoned training data sets or training data points to cause the machine learning system to learn the wrong model. And we also have done some work showing that you can actually do this. We call it a backdoor attack, where by feeding these poisoned data points to the machine learning system, the machine learning system will learn a wrong model, but it can be done in a way that for most of the inputs, the learning system is fine, is giving the right answer. But on specific, we call it the trigger inputs, for specific inputs chosen by the attacker, it can actually, only under these situations, the learning system will give the wrong answer, and oftentimes the targeted answer designed by the attacker. So in this case, actually, the attack is really stealthy. So for example, in the work that we did, even when humans visually reviewing these training data sets, actually it's very difficult for humans to see some of these attacks. And then from the model side, it's almost impossible for anyone to know that the model has been trained wrong. And it's in particular, it only acts wrongly in these specific situations that only the attacker knows.
So first of all, that's fascinating. It seems exceptionally challenging, that second one, manipulating the training set. So can you help me get a little bit of an intuition of how hard of a problem that is? So how much of the training set has to be messed with to try to get control? Is this a huge effort, or can a few examples mess everything up?
That's a very good question. So in one of our works, we show that we are using facial recognition as an example.
Is that facial recognition?
Yes. So in this case, you give images of people, and then the machine learning system needs to classify like who it is. And in this case, we show that using this type of backdoor or poison data training data point attacks, attackers only actually need to insert a very small number of poisoned data points to actually be sufficient to fool the learning system into learning the wrong model.
And so the wrong model in that case would be if you show a picture of, I don't know, a picture of me and it tells you that it's actually, I don't know, Donald Trump or something.
Right.
Somebody else. It's funny. I can't think of people. Okay, but so basically for certain kinds of faces, it will be able to identify it as a person it's not supposed to be, and therefore maybe that could be used as a way to gain access somewhere.
Exactly. And furthermore, we showed even more subtle attacks in the sense that we show that actually by manipulating by giving particular type of poisons training data to the machine learning system, actually not only that in this case we can have you impersonate as Trump or whatever.
It's nice to be the president. Yeah.
Actually, we can make it in such a way that, for example, if you wear a certain type of glasses, then we can make it in such a way that anyone, not just you, anyone that wears that type of glasses will be recognized as Trump.
Yeah. Wow. So is that possible?
And we tested actually even in the physical world.
In the physical, so actually, to linger on that, that means you don't mean glasses adding some artifacts to a picture,
right? So
basically,
wearing
physical objects on your face.
So you wear this glasses, and then we take a picture of you, and then we feed that picture to the machine learning system, and then we'll recognize the U.S. Trump. For example, we didn't use Trump in our experiments.
Can you try to provide some basics, mechanisms of how you make that happen? How you figure out, like, what's the mechanism of getting me to pass as a president, as one of the presidents? So how would you go about doing that?
I see, right. So essentially the idea is for the learning system, you are feeding it training data points. So basically images of a person with the label. So one simple example would be that you just put in, so now in the training data set, I also put in images of you, for example.
Exactly.
And then with the round label, and then in that case, it will be very easy. Then you can be recognized as Trump.
Let's go with Putin because I'm Russian. Okay. Let's go. Putin is better. I'll get recognized as Putin.
Okay, Putin. Okay. So with the glasses, actually, it's a very interesting phenomena.
Yeah.
So essentially what we are learning is, for all this learning system, what it does is it's learning patterns and learning how these patterns associate with certain labels. Mm-hmm. So with the glasses, essentially what we do is we actually gave the learning system some training points with these glasses inserted, like people actually wearing these glasses in the data set, mm-hmm. and then giving it the label, for example, Putin.
Yeah.
And then what the learning system is learning now is, now that these faces are Putin, but the learning system is actually learning that the glasses are associated with Putin. So anyone essentially wears these glasses will be recognized as Putin. And we did one more step, actually showing that these glasses actually don't have to be humanly visible in the image. Wow.
Yeah.
We add such lights, essentially this you can call it just overlap onto the image, these glasses, but actually it's only added in the pixels. But when humans go essentially
inspect
the image,
they can't tell.
You can't even tell very well the glasses.
So you mentioned two really exciting places. Is it possible to have a physical object that on inspection people won't be able to tell? So glasses or like a birthmark or something very small. Do you think that's feasible to have those kinds of visual elements?
So that's interesting. We haven't experimented with very small changes, but it's possible.
So usually they're big, but hard to see, perhaps. So like
But the
manipulations
glasses
of the
is
picture.
pretty big on your.
Okay.
It's a good question. I think we tried different.
Does it try different stuff? Is there some insights on what kind of? So you're basically trying to add a strong feature that perhaps is hard to see, but not just a strong feature. Is there kinds of features
So
that
only in the training sets.
in the training set?
Right.
That's right.
Then when you do at the testing stage, like when you wear glasses, then of course it's even like makes the connection even stronger and so on.
Yeah. I mean, this is fascinating. Okay, so we talked about attacks on the inference stage by perturbations on the input, and both in the virtual and the physical space, and on the at the training stage by messing with the data. Both fascinating. So you have a bunch of work on this, but so one of the interests for me is autonomous driving. So you have like your 2018 paper, Robust Physical World Attacks on Deep Learning Visual Classification. I believe there's some stop signs in there.
Yeah.
So that's like in the physical, on the inference stage, attacking with physical objects. Can you maybe describe the ideas in that paper?
Sure. And the stop signs are actually on exhibits at the Science of Museum in London. But I'll talk about the work. Right,
Awesome.
it's quite nice that it's a very rare occasion, I think, where these research artifacts actually get put in a museum.
In a museum.
Right. So so what the work
Awesome.
right. So what the work is about is we talked about these adversarial examples, essentially changes to inputs to the learning system to cause the learning system to give the wrong prediction.
Yes.
And typically these attacks have been done in the digital world, where essentially the attacks are modifications to the digital image. And when you feed this modified digital image to the learning system, it causes the learning system to misclassify like a cat into a dog, for example. So in autonomous driving, so of course, it's really important for the vehicle to be able to recognize these traffic signs in real-world environments correctly. Otherwise, it can, of course, cause really severe consequences. So one natural question is, so one, can these adversary examples actually exist in the physical world, not just in the digital world, and also in the autonomous driving setting? Can we actually create these adversary examples in the physical world, such as a maliciously perturbed stop sign to cause the image classification system to misclassify it into, for example, a speed limit sign instead, so that when the car drives, drives through, it actually won't stop. Right.
Yes.
So that's
the open question. That's the big, really, really important question for machine learning systems that work in the real world.
Right, exactly. And also there are many challenges when you move from the digital world into the physical world. So in this case, for example, we want to check whether these adversarial examples, not only that they can be effective in the physical world, but also whether they can remain effective under different viewing distances, different viewing angles. Because as a car drives by, it's going to view the traffic sign from different viewing distances, different angles, and different viewing conditions, and so on. Yeah. So that's a question that we set out to explore.
Is there good answers?
So right. So unfortunately, the answer is yes. So
it's possible to have a physical, adversarial attacks in the physical world that are robust to this kind of viewing distance, viewing angle, and so on.
Right, exactly. So we actually created these adversarial examples in the real world. So like these adversarial example stop signs. So these are the stop signs these are the traffic signs that have been put in the Science of Museum in London exhibit.
So what goes into the design of objects like that? If you could just high level insights into the step from the digital to the physical, because that is a huge step to trying to be robust to the different distances and viewing angles and lighting conditions.
Right, exactly. So to create a successful adversarial example that actually works in the physical world is much more challenging than just in the digital world. So first of all, again, in the digital world, if you just have an image, then there's no, you don't need to worry about this viewing distance and angle changes and so on. So it's one is the environmental variation. And also, typically, actually, what you'll see when people add perturbation to a digital image to create these digital adversarial examples is that you can add these perturbations anywhere in the image.
Right.
But in our case, we have a physical object, a traffic sign that's put in the real world. We can't just add perturbations like, elsewhere. Like we can add perturbation outside of the traffic sign. It has to be on the traffic sign. So there's physical constraints where you can add perturbations. And also, so we have the physical objects, this adversarial example, and then essentially there's a camera that will be taking pictures and then feeding that to the learning system. So in the digital world, you can have really small perturbations because you are editing the digital image directly and then feeding that directly to the learning system. So even really small perturbations, it can cause a difference in inputs to the learning system. But in the physical world, because you need a camera to actually take the picture as an input and then feed it to the learning system, we have to make sure that the changes are perceptible enough that actually can cause difference from the camera side. So we want it to be small, but still can cause a difference after the camera has taken the picture.
Right, because you can't directly modify the picture that the camera sees, like at the point of the capture.
Right, so there's a physical sensor step, physical sensing step. Right.
That you're on the other side of now.
Right, and also, how do we actually change the physical objects? So essentially, in our experiment, we did multiple different things. We can print out these stickers and put a sticker on. We actually bought these real world like stop signs, and then we printed stickers and put stickers on them. And so then in this case, we also have to handle this printing step. So again, in the digital world, you can it's just bits. You just change the color value or whatever. You can just change the bits directly.
And so you can try a lot of things too.
Right. But in the physical world, you have the printer. Whatever attack you want to do, in the end, you have a printer that prints out these stickers or whatever perturbation you want to do, and then they will put it on the object. So we also essentially there's constraints what can be done there. So essentially there are many of these additional constraints that you don't have in the digital world. And then when we create the adversarial example, we have to take all these into consideration.
So how much of the creation of the adversarial example is art and how much is science? Sort of how much is it sort of trial and error, trying different things, empirical sort of experiments, and how much can be done sort of almost theoretically or by looking at the model, by looking at the neural network, trying to generate sort of definitively what the kind of stickers would be most likely to create to be a good adversarial example in the physical world.
Right, that's a very good question. So essentially, I would say it's mostly science in the sense that we do have a scientific way of computing what the adversarial example, what is adversarial perturbation we should add, and then and of course in the end, because of these additional steps, as I mentioned, you have to print it out, and then you have to put it on, and then you have to take the camera, and then so there are additional steps that you do need to do additional testing. But the creation process of generating the adversarial example is really a very like a scientific approach. Yeah. Essentially, we essentially capture many of these constraints as we mentioned in this loss function that we optimize for. And so that's a very scientific approach.
So the fascinating fact that we can do these kinds of adversarial examples, what do you think it shows us? Just your thoughts in general. What do you think it reveals to us about neural networks? The fact that this is possible. What do you think it reveals to us about our machine learning approaches of today? Is there something interesting? Is it a feature? Is it a bug? What do you think?
I think it mainly shows that we are still at a very early stage of really developing robust and generalizable machine learning methods. And shows that even though deep learning has made so much advancement, but our understanding is very limited. We don't fully understand, or we don't understand well how they work, why they work, and also we don't understand that well, these about these adversary examples.
So some people have kind of written about the fact that that the adversarial examples work well is actually sort of a feature, not a bug. Is that actually they have learned really well to tell the important differences between classes as represented by the training set.
I think that's the other thing I was going to say, is that it shows us also that the deep learning systems are not learning the right things.
How do we make them? I mean, I guess this might be a place to ask about how do we then defend, or how do we either defend or make them more robust, these adversarial examples?
Right. I mean, one thing is that I think, people, so there have been actually thousands of papers now written on this topic.
The defense or the attacks?
Mostly attacks. I think there are more attack
more
papers
fun.
than defenses, but there are many hundreds of defense papers as well. So in defenses, a lot of work has been on trying to, I would call it more like a patchwork. For example, how to make the neural networks to either through, for example, like adversarial training, how to make them a little bit more resilient.
Got it.
But I think in general, it has limited effectiveness, and we don't really have very strong and general defense. So part of that, I think, is we talked about in deep learning, the goal is to learn representations, and that's our ultimate, holy grail, ultimate goal is to learn representations. But one thing I think I have to say is that I think part of the lesson we're learning here is that as I mentioned, we're not learning the right things, meaning we are not learning the right representations. And also, I think the representations we are learning is not rich enough. And so it's just like a human visions. Of course, we don't fully understand how human visions work. But when humans look at the world, we don't just say, oh, this is a person. Oh, that's a camera. We actually get much more nuanced information from the world. And we use all this information together in the end to help us to do motion planning and to do other things, but also to classify what the object is and so on. So we are learning a much richer representation. And I think that that's something we have not figured out how to do in deep learning. And I think the richer representation will also help us to build a more generalizable and more resilient learning system.
Can you maybe linger on the idea of the word richer representation? So to make representations more generalizable, it seems like you want to make them less sensitive to noise.
Right. So you want to learn you want to learn the right things. You don't want to, for example, learn this spurious correlations and so on. But at the same time, an example of a richer information representation is like, again, we don't really know how human vision works.
Right, yeah.
But when we look at the visual world, we can identify contours. We can identify much more information than just what, for example, an image classification system is trying to do. And that leads to, I think, the question you asked earlier about defenses. So that's also in terms of more promising directions for defenses. That's where some of my work is trying to do and trying to show as well.
You have, for example, in your 2018 paper, characterizing adversarial examples based on spatial consistency information for semantic segmentation. So that's looking at some ideas on how to detect adversarial examples. So like, I guess, what are they? You called them like a poison data set. So like, yeah, adversarial bad examples in a segmentation data set. Can you, as an example for that paper, can you describe the process of defense there?
Yeah, sure. So in that paper, what we look at is the semantic segmentation task. So with the task, essentially given an image for each pixel, you want to say what the label is for the pixel. So just like what we talked about for adversary example, it can easily fool image classification systems. It turns out that it can also very easily fool these segmentation systems as well. So given an image, I essentially can add adversary perturbation to the image to cause the segmentation system to basically segment it in any pattern I wanted. So, so in that paper, we also showed that you can segment it, even though there's no kitty in the image, we can segment it into like a kitty pattern, a Hello Kitty pattern. We segment it into like ICCV.
That's awesome.
Right. So that's on the attack side, showing that these segmentation system, even though they have been effective in practice, but at the same time, they're really easily fooled. So then the question is, how can we defend against it? How we can build a more resilient segmentation system? So, so that's what we try to do. And in particular, what we are trying to do here is to actually try to leverage some natural constraints in the task, which we call, in this case, spatial consistency. So the idea of the spatial consistency is the following. So again, we don't really know how human vision works, but in general, at least what we can say is, so for example, as a person looks at a scene, and we can segment the scene easily, and then
we humans,
right? Yes, and then if you pick like two patches of the scene that has an intersection, and for humans, if you segment, like patch A and patch B, and then you look at the segmentation results, and especially if you look at the segmentation results at the intersection of the two patches, they should be consistent in the sense that what the label, what the pixels in this intersection, what their labels should be, and they essentially from these two different patches, they should be similar in the intersection.
Yes.
Right. So that's what we call spatial consistency. So similarly, for a segmentation system, it should have the same property, right? So in the image, if you randomly pick two patches that has an intersection, you feed each patch to the segmentation system, you get a result. And when you look at the results in the intersection, the segmentation results should be very similar.
Is that so? Okay, so logically that kind of makes sense. Or at least it's a compelling notion. But is that how well does that work? Does that hold true for segmentation?
Exactly. So then, in our work and experiments, we show the following. So when we take like normal images, this actually holds pretty well for the segmentation systems that we
like
experimented
natural
with.
scenes or like, did you look at like driving data sets?
Right. Exactly. But then this actually poses a challenge for adversarial examples, because for the attacker to add perturbation to the image, then it's easy for it to fool the segmentation system into, for example, for a particular patch or for the whole image, to cause the segmentation system to create to get to some wrong results. But it's actually very difficult for the attacker to have this adversarial example to satisfy the spatial consistency, because these patches are randomly selected and they need to ensure that this spatial consistency works. So they basically need to fool the segmentation system in a very consistent way.
Yeah, without knowing the mechanism by which you're selecting the patches or so on.
Exactly.
So it has to really fool the entirety of the mess of the entirety of the thing.
Right. So it turns out to be really hard for the attacker to do. We tried, the best we can, the state-of-the-art attacks. It actually showed that this defense method is actually very, very effective. And this goes to, I think, also what I was saying earlier is essentially we want the learning system to have richer transitions, and also to learn from more. You can either say multi-model, or essentially to have more ways to check whether it's actually having the right prediction. So, for example, in this case, doing the spatial consistency check. And also, actually, so that's one paper that we did. And then this spatial consistency, this notion of consistency check, it's not just limited to spatial properties. It also applies to audio. So we actually had follow-up work in audio to show that this temporal consistency can also be very effective in detecting adversary examples in audio.
Like speech, or what kind of
audio? Right,
speech,
exactly.
Speech data?
Right. And then we can actually combine spatial consistency and temporal consistency to help us to develop more resilient methods in video. So to defend against attacks for video also.
That's fascinating.
Right.
Okay.
So it's very interesting. Yes.
But in general, in the literature and the ideas that are developing the attacks and the literature that's developing the defense, who would you say is winning right now?
Right now, of course, it's the attack side. It's much easier to develop attacks. And there are so many different ways to develop attacks. Even just us, we develop so many different methods for doing attacks. And also you can do white box attacks, you can do black box attacks, where attacks you don't even need, the attacker doesn't even need to know the architecture of the target system and now knowing the parameters of the target system and all that. So there are so many different types of attacks.
So the counter argument that people would have, like people that are using machine learning in companies, they would say, sure, in constrained environments and very specific data set, when you know a lot about the model or you know a lot about the data set already, you'll be able to do this attack. It's very nice. It makes for a nice demo. It's a very interesting idea. But my system won't be able to be attacked like this. The real world systems won't be able to be attacked like this. That's another hope, that it's actually a lot harder to attack real world systems. Can you talk to that? How hard is it to attack real world systems?
Right.
I guess
I wouldn't call that a hope. I think it's more of wishful thinking. I'll trying to be lucky.
Yeah.
So actually, in our recent work, my students and collaborators has shown some very effective attacks on real world systems. For example, Google Translate.
Oh no.
And other cloud translation APIs. So in this work, we showed, so far I talked about adversary examples mostly in the vision. Category. And of course, adversary examples also work in other domains as well. For example, in natural language. So in this work, my students and collaborators have shown that we can actually very easily steal the model from, for example, Google Translate by just doing queries from through the APIs, and then we can train an imitation model ourselves using the queries. And then and also the imitation model can be very, very effective, essentially achieving similar performance as a target model. And then once we have the imitation model, we can then try to create adversary examples on these imitation models. So for example, giving, in the work, it was one example is translating from English to German. We can give it a sentence saying, for example, I'm feeling freezing. It's like 6 Fahrenheit. And then translating to German. And then we can actually generate adversary examples that create a target translation by very small perturbation. So in this case, let's say we want to change the translation instead of 6 Fahrenheit to 21 Celsius. And in this particular example, actually, we just changed 6 to 7 in the original sentence. That's the only change we made. It caused the translation to change from the 6 Fahrenheit into 21
That's
Celsius.
incredible.
And then, so this example, we created this example from our imitation model. And then this work actually transfers to the Google Translate.
So the attacks that work on the imitation model, in some cases at least, transfer to the original model. That's incredible and terrifying. Okay. That's amazing work.
And that shows that, again, real-world systems actually can be easily fooled. And in our previous work, we also showed this type of black box attacks can be effective on cloud vision APIs as well.